Welcome back, everybody. In the last lecture, we had a general introduction on acid-base chemistry, and more specifically, we focused on Brønsted acid-base concept. Now, we have learned that a Brønsted acid is a proton donor and a Brønsted base is a proton acceptor. Acid and base are in equilibrium, and the strength of the acid or the base is determined by the equilibrium constant K, or its negative log value, which is the pK value. Now, today we will continue and talk about specific types of acids. We have already encountered polyprotic acids. These acids contain multiple protons which can dissociate. Here is an example, which is phosphoric acid. And as you can see from the formula, there are 3 hydrogen atoms in the formula unit. Now, phosphoric acid is an acid, as it suggests, and it can react with water by protonating the water to the hydronium ion. Now, we can see in the first equation that the first proton dissociates and protonates 1 molecule of water. This particular equilibrium can be called a Ka1. We still have 2 protons after dissociation of the first proton that can further be donated to bases. In the second equation, we donate the second proton to the water and we form a dianion. And there's still 1 proton left, and so in the third step we can fully dissociate phosphoric acid to the phosphate anion, and we have essentially removed 3 protons. Now, each of these steps has its own equilibrium constant, and we can call them K1, K2, and K3. In relation to each of these equilibrium constants, there is obviously the negative log value, and so we have 3 respective pKa values as well. And each of this would change by about 5 units. And that is quite understandable because we know the smaller the pKa value, the stronger is the acid. And here we can see with successive loss of a proton, the acid becomes weaker and weaker. And the decrease in acidity is consistent with an electrostatic model because we have a buildup of negative charges here along the line. And to remove a proton from a negatively charged species, it is obviously more difficult, and therefore the acid would drop in strength with each deprotonation process. Now, phosphoric acid is also an example of a so-called oxoacid. And here you can see examples of various oxoacids, and you can see that they always contain oxygen. You can also see here the pKa values of these respective acids noted down. Now, the general formula for an oxoacid is EON OHM. So we have n numbers of oxygen, which is bound to the central atom E, which do not contain any hydrogen. In addition, because we are talking about Brønsted acids here, we need to have protons there as well. And so we have also a certain number m of functions which correspond to OH, which means oxygen containing hydrogen atoms. Now, the dissociation obviously must appear from this unit here. For the first examples shown here, you note that there is actually no oxygen bound to the central atom that has no hydrogen. So the number n is equals to 0. Now we have examples here, and each of them contain essentially 1 oxygen atom bound to the central atom that doesn't carry a hydrogen atom. So all these examples would fulfill the situation when n equals 1. And now you can also see that compared to the n equals 0 series, the pKa, or the first pKa value, is essentially much lower than those in the first series. We can continue along the line, and now we can have here acids with 2 oxygen that are free of hydrogen atoms. And again, you see a further drop of the pKa values of these respective acids. And now we are even in the negative range. With n equals 3, we have extremely strong acids. Now, the reason behind that is quite clear because oxygen, as you may know, is electronegative. So it's essentially the second most electronegative atom, only second to fluorine. And its electronegativity would withdraw electron density away from the central atom and therefore polarizing the OH bond much more so than in cases where there are no oxo present. Now, with this electron withdrawing effect, you increase the acidity of the OH function, and therefore dissociation of the proton becomes much more easier with increasing amounts of hydrogen-free oxygen. Now here we see a table where the first dissociation constants of selected oxoacids are noted down. You have oxoacids based on nitrogen, sulfur, and even chlorine. So these are the central atoms. The number of hydrogen-free oxygen would decrease or increase according to this table. Again, you can see with a larger number of N, you have smaller pKa values. So for the third example, which means the oxoacids derived from chlorine, you have 4 examples. So you can change, as you can see here in the formula, the number of hydrogen-free oxygens, and you end up with a significant drop of the pKa values. Now the pKa1, which means the first dissociation constant in case of polyprotic acid, decreases as the number of hydrogen-free oxygen atoms increases. So you can estimate that using the Bell's rule, and take note that this only applies for neutral acids, right? So neutral oxoacids of this particular general formula, and if you know N, you can estimate the pKa value of this particular acid using this formula, whereby pKa, the first pKa, equals to about 8 minus 5N. This rule is sometimes also referred to Pauling's rule, and so you can also test it already in this table here. For example, N equals 0, you essentially have a prediction of about 8 in terms of pKa, and you can see in actuality you are having a pKa value measured at 7.2, so this is quite close. Now this is an estimation again. For N equals 1, you have 8 minus 5, that is 3. And again, the estimation is quite close, so 2 is not too bad. So you can basically use this rule to estimate oxoacids. Now Bell's rule, again, can be used to estimate the pKa values of oxoacids which are neutral, which means we are talking about a pKa1, which means the first dissociation of the oxoacid. With polyprotic acids, as we have seen in the phosphoric acid example before, each deprotonation leads actually to a weaker acid. And we have explained that already by the buildup of the negative charge, and where removal of a second proton from a negatively charged species must be much more difficult. So this is summarized here again. After the first dissociation of a polyprotic acid, the number of hydrogen-free oxygen atoms increases to N plus 1. Now this hydrogen-free oxygen atoms cannot be confused with those in the Bell's rule. These hydrogen-free oxygen atoms actually carry a negative charge. So the negative charge of the overall molecule increases, which hampers the successful second deprotonation. So the greater number of oxygen atoms in the conjugated base, the more the negative charge of the anion can be spread out, because you have lone pairs at each of the oxygen atoms. And the more oxygen you have, the more stable is the negative charge spread out over the whole molecule. So here we can see an example of the nitrate anion, which is the anion of nitric acid. After its removal of the proton, you have 1 negative charge, but you have now 3 oxygen atoms that do not have any hydrogen left. And so all of them become equivalent, and so they share this single negative charge. In other words, the negative charge here is distributed throughout the molecule, and essentially each oxygen would carry a 1/3 of the negative charge. So we call that a delocalization of the negative charge. The negative charge of the nitrate anion is delocalized uniformly over the p bonding system. So again, the successive pKa values of polyprotic acids, which means pKa1, pKa2, etc., those with N greater than 1, increases by approximately 5 units for each successive deprotonation. So for a polyprotic acid again, each deprotonation would weaken the acid by about 5 pKa units. Now this slide shows a specific example of a Brønsted acid. These are called Aqua acids. And as the name suggests, they contain water. And essentially, these aqua acids are equated cations, and because of the water molecule that is still present in this molecule, you actually have protons that you can remove. So they can act as a Brønsted acid as well. These aqua acids are quite interesting species because they already combine concepts of the Lewis acid-base theory with the Brønsted acid-base theory. Now, later when we talk more about Lewis acid-base theory, you will understand more. But at the moment, we will just focus as this aqua acid as a whole unit here. So it looks for you maybe rather complicated at the moment, but it's not that because I walk you through this example. Now, when you dissolve sodium chloride, everybody knows this is your salt that you're consuming on a daily basis. And if you take these white crystals of sodium chloride and you dissolve it in water, then you generate already an aquated cation. So the sodium chloride or the sodium chloride lattice will break down, and each of the sodium cations will be surrounded by water molecules. And because sodium is positively charged, then you have a Coulomb interaction with the negatively charged oxygen. In water molecule, the oxygen atom carries a partial negative charge. Okay, so this is not a true negative charge because overall the water molecule is obviously neutral, but you can also say that the electron density is more located on the oxygen as compared to the hydrogen, and so the oxygen carries a partial negative charge here. On the other hand, the hydrogen atoms, which is not depicted here, would carry the partial positive charge. So now the partial negative charge of the oxygen is attracted to the positive charge of the sodium. And so in this example, 6 water molecules essentially have some sort of interaction with the sodium cation. This particular interaction is already giving rise to a so-called Lewis acid-base adduct, because a Lewis base, as we will learn later on in more detail, is an electron donor, and a Lewis acid is an electron acceptor. Now, the oxygen uses its lone pairs of electrons to interact with the sodium. So it donates essentially electron density towards the sodium ion, and therefore it stabilizes this moiety in water. Now, this is what happens when you dissolve sodium chloride in water. And of course, the chloride anions will also have interaction with the water molecules, and they interact obviously with the partial positively charged hydrogen atoms of the water molecule, and they engage in something we call hydrogen bonding. But this is not really important to the aqua acid in itself. So this 6 coordinated sodium cation forms a Lewis acid-base adduct, and if you have these water molecules around, you can see that you actually can remove protons there as well. And this whole thing is the first hydration shell. Now, when you use sodium chloride, right, which is derived from a very strong acid, which means HCl, and a very strong base, sodium hydroxide, if you mix these two, of course, you generate water and sodium chloride. And so the salt of a strong acid and a strong base is very stable. And so when you dissolve it in water, you do not change the pH much. So this is just a hydrated cation. But when we move away from the main group to the transition metals, then we can generalize the cations as Mn+. And we do the same thing. We dissolve these sort of transition metal salts in water. And what we get are these hydrated transition metal ions. And so now the transition metal ions with the higher positive charge here would have a much stronger interaction with the water. And so these are called coordination or dative metal-ligand interactions. And so through their electron withdrawal along this line here, they actually polarize the water molecules much more so than, for example, sodium can do. And so the polarization along this line towards the metal center here would polarize these hydrogen, and essentially you have a more acidic species in solution. So again, these are called complexes or adducts, and they are a result of Lewis acid-base reactions, but they themselves as a whole unit are actually aqua acids, and they can act as proton donors to act as Brønsted acids. Here we have a specific example. We can take a copper 2 salt and dissolve it in water. And what you get here is this hexa aqua copper 2 complex. And the arrangement of the oxygen atoms of the water molecules around the central metal gives rise to a shape we call an octahedron. So the geometry of such aqua acids is often octahedral in geometry. Now, these metal-water complexes can act as Brønsted acids by loss of hydrogen or protons from a coordinated water molecule. And this is demonstrated in this particular equation here. We have our hexa-aqua complex with a specific metal center. And dependent on the charge of this metal ion, we have N plus here as a superscript. And the AQ basically indicates that this whole species is in water. And so this whole unit here is surrounded by many additional water molecules. And so this species can actually interact with the surrounding water molecules, and hydrolysis or deprotonation can take place. And so one of these water molecules that are directly bound to the metal center can lose its hydrogen atom or its proton and protonate a water molecule to the hydronium ion. And by loss of a proton, it will form a OH minus species. And because you have converted essentially a neutral water molecule into a negatively charged hydroxide ion, obviously the overall charge of this species indicated in square bracket is changing. So the positive charge is reduced by 1 upon deprotonation of one bound water molecule. So the position of this equilibrium depends on the degree of the OH bond polarization, which in turn depends on the charge of the metal ion. So you can imagine that the larger the positive charge of the metal ion, the stronger will be your aqua acid. Now this slide demonstrates that again, and we can conclude when water coordinates to a Mn plus cation, the charge is withdrawn towards the metal center, which means the negative charge of the oxygen atoms, right? And therefore the OH bond is polarized, leaving the hydrogen atoms of the water molecule with a greater partial positive charge than in the water molecule which is not bound to a metal cation. So this is demonstrated here. You have a partial negative charge here of the oxygen that donates to the metal center, and then it withdraws additional electrons through this interaction away from the hydrogen, and so the hydrogen will become more delta plus, and so bond dissociation is facilitated here, and it can react with this water molecule which can receive the proton, and so this one acts as a Brønsted base. This is your aqua acid, and so after occurrence of this first deprotonation, you essentially convert this water molecule, which was initially bound to the metal ion, to a hydroxo species, and you generate your hydronium ion. So you convert essentially an aqua complex into a hydroxo complex. Here you can see different examples of aqua acid and hydroxo acids and their relation to each other. Here you can see again 6 water molecules bound to a ion 3 cation. So the positive charge here 3 plus is coming from the ion 3 plus cation, which is then surrounded by 6 water molecules. So this is the particular formula for this species. Here we have an example involving tellurium as a center, and this tellurium is actually bound to 6 hydroxo anions. So these hydroxo anions bring a negative charge, and overall this molecule is neutral, which means your oxidation state here of the tellurium is tellurium 6 plus. So the 6 positive charge from the tellurium cation are nicely balanced by the 6 negative charges from the hydroxo anions. And so if you remove a proton from a hydroxo acid, you can actually end up with oxoacids. Again, aqua acids contain water molecules bound to the metal. Here we have hydroxo species bound to the central element, and here we have hydrogen-free oxo species. So this is a sulfuric acid molecule, and this belongs to this oxo acid. Sometimes you can actually have this occurring within kind of successively from a same species. So here we have a ruthenium complex bound with 2 water molecules, and L are additional species which we call ligands. These are just neutral additional species that are bound to the ruthenium, not of concern to the discussion of aqua acids. So the important part here is highlighted in blue. and you have a 4+ species, which means since L, as I mentioned just now, is neutral and water is neutral, you actually have a ruthenium 4+ center here. And so this ruthenium 4+ polarizes these two water molecules, and they can actually lose 2 protons. And so this species will be in equilibrium with the respective hydroxo species. So you convert by loss of 2 protons, these 2 water molecules or water ligands into 2 hydroxo ligands. And they still contain protons that can be removed. But of course, you have converted now 2 neutral ligands here into 2 anionic ligands. So the overall charge obviously will drop to 2+. And so by removal of 1 additional proton, you actually end up with a ruthenium complex, which has only 1 positive charge left. So here you have essentially an oxo acid, hydroxo acid, and an aqua acid. Now this slide shows the dependence of the pKa value, which means the acidity of the aqua acids, independence of the radius or the squared charge over the radius, and the response of the pKa values on these particular parameters. Here we can have metal ions from the group 1, and then we have metal ions of group 2. And obviously, metal ions in the group 2 will have an increased positive charge. So we have a 2+ species here compared to 1+ species in the first examples. And you can see that the pKa values of the group 1 metals are rather large. If you increase the charge, you can see the trend here is that it essentially slightly drops the pKa values of these aqua acids. And the radius also plays a role because it's reflected in this particular value here. And so with smaller and more charged species, you actually have an efficient drop of the pKa value. Now with this slide, we are concluding our lecture on Brønsted acid-base chemistry. And in the next lecture, we will be focusing on Lewis acid-base chemistry. See you then.